So this is a video on what a power series is, power series in general, how to make them, how to find new ones. So here's what a generic geometric series looks like. Instead of r for the ratio between successive terms, we're just going to use the variable x because we want to start to talk about these things as functions. Okay, so that's what it looks like. So think about what the terms of this thing are. They're 1, right, x to the 0, plus x squared, plus x cubed, plus x to the 4th, so on and so forth. Okay, so that's just the simplest possible geometric series we can imagine, but instead of a specific ratio, we're just looking for every term is just x times the last term. So what does that look like? It looks like a polynomial, right? It looks like a very simple polynomial. The only thing that's different about it is that it has infinite terms. So essentially, that's what a power series is. It's a polynomial of infinite degree. Okay, so really, I'm just going to define it like that. It's just an infinite degree polynomial. It can skip terms. It can obviously have coefficients. It can have more going on here. This is just the simplest one, and so the one we build a foundation off of. And it's a function, and so it has a domain. And we've seen when we studied geometric series that a geometric series will always converge if the ratio between successive terms is strictly between -1 and 1. Okay, that's just a fact of geometric series. We covered that. You should be cool with that. Okay, if the ratio between successive terms is a half or -1/2 or 0.99 or whatever, it will converge. If it's not, it won't. So we call that the domain of the function, right? This is a function. It's just a different kind of function because it has infinite terms, but it's just a polynomial. And any x we can stick into it is called its domain. And if we stick an x like 2 into it, it will not converge. So therefore, it doesn't really have any mathematical meaning. So this function is only ever defined for this, for if x is in this interval. Okay, if x is in that interval, it will converge. And because it's geometric, we actually know what it converges to. So think back to the formula for convergent geometric series. It converges to a over 1 minus r, but there's no a here. So a is just 1. And instead of the variable r, we're using the variable x. Right? So that's, again, nothing new. That's just a fact of geometric series. If x converges at all, it will converge to that number. Okay? But now, like, that's not a number, it's a function. It's the function 1 over 1 minus x. Okay, so that's just straight up the formula for convergent geometric series and what they actually sum to. So this green thing is the graph of 1 over 1 minus x. And this blue thing is the graph of literally just the first 2 terms of this. And we're going to build on that. So maybe hold off on sketching that if you're taking notes and just bear with me for a second. So that's the graph of just 1 plus x. It's just a straight line. In fact, it looks like a tangent line. That's exactly what it is. But it certainly hits the curve right here, and that's really all it does. Now what we're going to do is add terms. One more term. So that's the graph of 1 plus x squared. So literally just the first 3 terms of this thing. Look how it glues itself to the curve. Isn't that nice? Okay, so it's starting to glue itself to the curve. There's one more term. Now it's a cubic, 1 plus x squared plus x cubed. Now remember, this only applies for the x's in here, between -1 and 1. So for all the other x's out here, wherever, this concept doesn't even apply because the function, that's not in its domain. But you hopefully can see where I'm going with this. The more terms we add to it, the better it's going to look. There's the next term, looks even better. There's the next term, right? It's really glued itself to the curve here so that we almost can't distinguish between the two. It's almost like a tangent curve. It's like a different function that really fits nicely with the curve. I forget how far I went with this, but hopefully you can see my point. Okay, I went that far. So that is the case with every single power series we're going to make. We don't just say that, like, theoretically, mathematically, this equals this. It's true. These are the exact same function. And when you stretch it all the way out to infinity, they are exactly the same. If we just have, I mean, here we just have the first 8 terms, but already between -1 and 1, they're pretty much indistinguishable, right? So now imagine if we had the first 100 terms or 1,000 terms, okay? So if we can truly say that this polynomial stretches out to infinite degree, then we can truly say that these two things are exactly equal. Okay, so that's what a power series basically is. Its use is we can represent functions as polynomials. Any function, that's true. We can take any function and write it as a polynomial like this. Sometimes it's so hard that it's impractical, so we'll focus on the cases where it's not. Okay, so just like with limits, right, we can't graph all infinity terms because there's just no such thing. But in theory, it works. Okay. So you've done an example of this before. To actually find the domain of a power series, you use the ratio test to determine for which x values it converges. I'm going to give you another example just because you haven't seen that many. So here's one. And you maybe didn't call that a power series before, but that's what it is. So this is like x minus 3 to the 1 over 1 plus x minus 3 squared over 2 plus x minus 3 cubed over 3. Okay, so that's a polynomial. That's an infinite degree polynomial in the variable x. So to find the domain is the same thing. Maybe you've seen the term interval of convergence. It's finding whichever x values this works for. So here we go. So remember, it's the absolute value of the n plus 1th term over the nth term. Hopefully you've already covered these. So you know that you just flip over the nth term because you're dividing by a fraction. And then we have to clean everything up. So x minus 3 to the n plus 1 over x minus 3 to the n. There's just one factor of x plus 3 in the numerator that survives. And then we have the n survived and the n plus 1 survived. And now we have to think about what absolute values mean. N is always positive. Why is n always positive? Because it just is. Because n is the index of a series. So n goes 1, 2, 3, 4, 5, 6, 7, right? It can never be negative. So there's some theorem. If you have something inside of absolute values that can never be negative anyways, you can pull it outside. You don't actually have to. But to me, it's simpler to think about what happens next. Okay, so, and you just have to say that. That's not even really algebra. That's just what n is. So now, remember the ratio test says it's actually the limit of this. So that's kind of, if you watch my other video, that's kind of how I do the ratio test. First, I deal with the fraction-y stuff. Then I deal with the absolute values. And now I have to deal with the limit. Okay, so similar, like a property of limit says if there's something inside your limit that doesn't depend on the limit, or doesn't depend on n, then it can actually come outside the limit. So you can almost think of that as algebra. You're just kind of factoring it out outside. Right. And then you have to think about the limit of n over n plus 1. So I don't know how you are conceiving of that. I can just look at it and tell that that limit is 1 because the numerator and the denominator are the same degree and the coefficients of both are just 1. So, or just think about what happens when you plug a really big number into n over n plus 1. It's pretty close to 1, doesn't it? Okay, so it's like an asymptote. And then again, the x minus 3, the absolute value of x minus 3 doesn't care that n is going to infinity. So the limit does nothing to it. So the ratio test gives you absolute value of x minus 3. And then finally, the actual conclusion of the ratio test is that this thing has to be less than 1. Whatever this limit is, it has to be less than 1. So we've simplified everything. We found the limit. It's just absolute value of x minus 3. And now we have to figure out for what values of x is the absolute value of x minus 3 less than 1. So this is kind of algebra. So for the absolute value of something to be less than 1, that means that the something has to be between -1 and 1. To me, that's a lot easier of a way to even think about it, right? Of an absolute value type of inequality. It has to be less than 1 away from 0. So any number in there counts. And now you just add 3 to both sides. Not both sides, all sides, right? right? That's how you solve an inequality, okay? So if x is between 2 and 4, strictly, this sucker up here is convergent. The one thing that you hate that we don't know is what happens at the endpoints, and you just literally have to plug in the endpoints and test them if you care to do, which I'm going to tell you to do on a test, so you have to. Okay, so let's do it. So you just literally take 2 and 4 and plug them back into this original thing and see if it's convergent. So when x is 2, you're literally going, okay, 2 minus 3 to the n is, 2 minus 3 is negative 1. So this is just going to be negative 1 to the n over n. This should kind of look familiar. This is an alternating p-series, but it really doesn't matter that it's a p-series or whatever. By the alternating series test, it just straight up converges. So the alternating series test just says that if the individual terms themselves in absolute value, so ignoring the negative, if the terms themselves, so the terms for this are just like 1, a half, a third, a fourth, a fifth, those are decreasing to 0. Since it's alternating, that's all you need to say that it converges. Okay, so I'm just going to kind of say that and not prove it. You've done that though. The limit as n goes to infinity of 1 over n is 0, so this thing converges. If it weren't alternating, it would not converge. It's a harmonic series. Okay, so when x is 4, like I said, literally you just go back here. Okay, 4 minus 3 to the n is just 1 to the n, which is obviously just 1. So now this is actually the harmonic series. So this is a p series with p equals 1. So this is 1 plus a half plus a third plus a fourth plus a fifth. We've seen before, your book has a cute proof of it, that this series, what's so famous it has a name, the harmonic series, and yes, that is as in music theory. I could explain that too, but that's a whole nother topic. Is divergent. It does not converge. It diverges very slowly. So, okay, so it's a very famous divergent p-series. It's called the harmonic series. It's the cutoff for where p-series converge or not. So it just is. And we've seen it and it's established. So that's all we need to say. Okay, so that means the 2 gets let in, the 2 belongs in the club, and the 4 does not. Okay, so finally, the thing we've been trying to figure out this whole time, what kind of numbers are allowed into this function, this infinite degree polynomial, those kind of numbers. So that's the domain of the function. The 2 is included because when x is 2, it does converge, but when x is 4, it does not converge. So any kinds of numbers between 2 and 4, if you stick them in there, this function has some meaning. It's finite. Another word for the domain of a p-series, or I'm sorry, of a power series, is interval of convergence. So it gets its own name because it is its own thing. So every domain of every function is an interval. This is called the interval of convergence. Okay, so that's just a vocabulary word. Okay, so now back to just power series in general. A generic power series looks like that. It's the sum from n equals 0. N doesn't have to start at 0. Okay, it's just simplest if it does. To infinity of, okay, c sub n, that's a coefficient. That can be anything. That can be 1, 2, 3, pi, whatever. So that's just the nth coefficient times x minus a to the n. So like the last one we saw was x minus 3 to the n. In that case, n or a would be 3. That's what it's often very helpful to just expand it out and see what it looks like. So C0, remember, is just the 0th coefficient. It's just some number. C1 is just the first coefficient. C2 is just the second coefficient, on, and then it's okay. The first term has x minus a to the 0, so that's just 1, and then it's x minus a to the 1, x minus a squared, x minus a cubed. If a is just 0, this whole thing looks a lot simpler, but it won't always be. So in this case, when it's not just, when there is an a that's not 0, we say that it's centered about a, or we just say that it's a power series about a. So you can think of a as just the middle of where this function converges. And I'll explain that right now, because let's talk more generally about intervals of convergence. There are only 3 things that can possibly happen here. the first thing that can possibly happen is it only converges when x is a exactly. And think about that. If x were a exactly in this, every one of these x minus a to a powers would just be 0. So this is kind of like the trivial case. We don't really care about power series that qualify for this, okay? Because they're not interesting, because they're just C0. So it's just like, it's like finding a power series for just like a horizontal line. Who cares? The second possibility, which it can happen, and this is probably the coolest possibility, is when it literally converges for all x. So just picture the graphs I showed you before, how between -1 and 1 it looked like it was locking up very nicely. In this, if it were a power series in the second case, which we'll certainly see some of these, it literally converges for no matter what number you put into it. There's a couple of very famous ones of these. Well, famous as math functions go. Okay, so that's pretty cool. So the interval of convergence, in other words, is literally just every number, and the domain is like a normal function. It's just everything. And then the third case, which is the one we just saw, which looks complicated but isn't as complicated as it looks, is there's a positive number r. So think of r as a distance. There's some positive number, 2, 3, 5, whatever. The series converges if x is between a minus r and a plus r. So I'll show you a picture in a second, but just think about what that means. It means, okay, here's a, here's r this way, here's r that way. If x is anywhere between there and there, then it'll converge. So it's symmetrical. It's a symmetrical interval of convergence. And what you'll see is they always are. This is the third and final case. So that's what that looks like. Here's a. If x is exactly a, this whole thing becomes 0. So it certainly converges. In fact, it converges to that, right? But if x is anywhere between a plus r and a minus r, so within r of a, r has a name. It's called the radius of convergence. So I'll get to that in a second. Then it converges. So this is like intervals of convergence are always symmetrical, and they're always symmetrical about this number a. If a were 0, then it would just be like, okay, the interval of convergence is between -2 and 2 or something. Okay, if a is some other thing, it's really the same deal, like the one we just saw. The picture's about to disappear, I think. So draw it. It's helpful. No, it's not. So the word for r is the radius of convergence. Very cool, fancy math word. And it always applies. So in the second case, it's like the radius of convergence is infinity, kind of. And in the first case, it's like it's 0, because it only converges for one discrete number. In most normal cases, like the kind we're going to see, there is an interval of convergence that's symmetrical about this number a, or whatever the power series is centered about. So in the last example, now we have just these new words. The interval of convergence was 2 to 4, including 2. And remember, that was a power series centered about 3, because it was x minus 3 to a power. So you can see that this interval is symmetric about the number 3. And the width, essentially, like the distance from 3 to the ends of the interval, was just 1. Okay? So I'm probably just going to ask you, like, find the interval of convergence. You don't have to really say what the radius is, but you'll see that it's always there. Okay. Talking more generally, and this is where it gets pretty cool. We take our first power series, our just most basic power series that's literally just a geometric series with a ratio that can be whatever, as long as the ratio is between -1 and 1, because if it's not, it doesn't converge. We already established this in this very lecture, but if x is in there, then this thing converges, and not only that, but it converges to this function. We've seen plenty of series that we know converge, but we don't know what they converge to. With power series, they converge to a function, if they converge at all, and we know what it is. We always know what it is. It's cool. Okay, so if that's true, then this equals this, and again, just picture those graphs I showed you earlier, right, with the blue graph looking more and more like the orange graph or whatever. Okay, so these two things are in fact equal. If we don't write what n starts at and stops at, just assume that n starts at 0 and goes to infinity, because pretty much everything we're going to see is like that. Yeah, the only interesting series are infinite series. So this seems almost like it's too easy, but it's true. So we want to make more power series. This one's old, it's boring to us. So let's make some more. And a basic way to do that is by messing with this one. The next lecture is a more powerful and fancy way to make new power series. Okay, so just look at this little equation here. These two things are exactly equal. I want you to make a function or a power series that equals this function, 1 over 1 plus x squared. Why this one? No reason. It's just an example. Okay, so what you want to do is look at this and say, how can I turn this right side of the equation into this? And if you want to turn the right side of the equation into this, we essentially just have to replace this x with a negative x squared. So if I replace this x with a negative x squared, I get 1 over 1 minus negative x squared, or 1 plus x squared. So again, it almost seems too simple. You're just taking both sides of an equation and plugging something else in for x. So if I just agree with me here that if you plug negative x squared into this thing, you get this thing, the thing that you want. And you're more than welcome to do that as long as you do the same thing on the other side of the equation. So just take the x that lives in this series and replace it with negative x squared. Okay, this is literally just doing the same thing to both sides of an equation. In this case, that thing is substituting something else. Why that something else? Because that's just what you were asked to do. You were asked to turn this into this. Okay, so you see it now. This is 1 over 1 plus x squared. The parentheses are important. And this is just whatever it is. Well, this is negative 1 times x squared. So the negative 1 to the n is just that. That makes this series alternate. Right? These terms are going to flip back and forth between positive and negative. And then these exponents are going to multiply, so you're going to get x to the 2n. Like that. Hopefully you agree with my algebra here. So we're just doing algebra within a series. Okay, so I'm going to show you a graph again because I want you to believe this. This isn't just theoretical math stuff. These two things are the same thing. They are the same exact function. Once again, it's helpful to write out some terms of a series so you know what you're looking at. So when n is 0, this is just 1. When n is 1, this is negative x squared. When n is 2, this is positive x to the 4th. And right from there, you can probably just extrapolate and just write the rest of the series because you get patterns, right? So it's plus x to the 4th minus x to the 6th plus x to the 8th minus x to the 10th, on and on and on, literally forever. Okay, so that's a new power series that only has even powers. And not only that, but they alternate. The terms, this is an alternating power series. Cool. So here's the graph of 1 over 1 plus x squared. It's called like a witch's hat function. It looks like a bell curve. It's not a bell curve, but it looks like one, although we'll deal with those. And here's the other thing. So I just randomly decided to graph the first 5 terms of that. Could have graphed more or less, but I think the first 5 gives a pretty good picture of what's happening. Between negative 1 and 1, these two functions are exactly the same. And the more terms I add to that, the better it gets. I encourage you to graph these on your own when you find them, because that's really a check. If I tell you that a power series equals like sine of x or something, and you're like, what? It can't. Just graph them both. You'll see. They do. They're exactly the same. Okay, so more terms would make it better. Infinite terms would make it perfect. But once again, only between negative 1 and 1, because we started with a power series that had that as its interval of convergence or its domain. So you don't change the domain when you mess with it like this. Kind of. Okay, so that's it. Just note that they have the same domain. Now, at the endpoints, it might be a little bit different, but we don't really have to deal with that. Here's another way of doing that. So it's just about manipulating both sides of an equation. A cooler way to do that is to take the derivative of both sides of the equation, or actually take the integral of both sides of the equation. So this is just me saying you can do that. So you don't really have to worry about this, but the interval conversions will be the same, except maybe at the endpoints of the interval, which you would just, again, have to guess and, well, not guess, but just check, plug them in. So, quick example. So we always were starting with that same relationship we started with. This is the known thing from geometric series. So if these two things are equal, just take the derivative of both sides of the equation and see what you get. So when you're taking the derivative of a power series, you can certainly go term by term, or you can look at a pattern. So you just do the same thing every term. So you know that the derivative of x to the n is nx to the n minus 1. That's just a straight up power rule. And then, so we're just taking the derivative of this side as well. I just rewrote it as 1 minus x to the negative 1 because you should. It's just good derivative habits. So this is just the power rule. The derivative of x to the n is nx to the n minus 1. This is a little chain rule business, so it's power rule times, don't forget about the derivative of the inside, which is actually negative 1, which actually just, as you can see, flips this back into being positive. So you can simplify that a little bit to 1 over 1 minus x squared. Okay, so that's a true. 1 over 1 minus x squared is, again, it's nice to write out the terms of this thing. Now you might say, where did the 0th term go? Well, it's just 0. So it doesn't matter if you start this series at 0 or 1. Sometimes that will matter, and it's really annoying. Okay, but for this, the 0th term just has no meaning, so it goes away. So this is 1 plus 2x plus 0 squared plus 4x cubed plus 5x to the 4th. So, right, what does that look like? It looks like derivatives of powers, which is really what it is. It's just a polynomial comprised of like all derivatives of x to a power. And it's weird to say, but that just equals this function. I'll show you. Yeah, there they are. So 1 over 1 minus x squared does have an asymptote here, but that's okay because the power series isn't defined there anyways. It's just defined between negative 1 and 1. You can see the orange curve and the blue curve just in here, just with the first 5 terms, are matching up quite nicely. Okay, so if I showed you the first 10 terms, it would match up more nicely here. And a funny thing about power series is also the same with regular series. Some of them converge super fast, like they just snap to it, and some of them either converge or diverge very slowly. And it's kind of just a case-by-case basis. Once you see the one for e to the x, you're going to be like, my God, it equaled it like instantly. And it does. E to the x is obviously a very special function in mathematics, and we'll see the power series for that. All right, one more, yes. Let's find one for arctan. Again, why? No reason. It's just one we can get using only the tools we have. And it seems like it's out of left field because it's like an inverse trig function. Why that? Well, because it's cool. So the only reason we can do this, we can't build it up from the ground up, in this case at least, is that we already have a series for 1 over 1 plus x squared. What the heck do those two things have to do with each other? You know what they do. This is the derivative of arctan. So we built this. Now, if you integrate this, you get arctan, right? Which means if you take the power series for this and integrate it, you should get an equivalent power series to arctangent, and you do. Okay, that's the key. So here it is. This is the one we found 2 examples ago. No, just one example. No, yeah, 2 examples ago. So we just replaced our original one with, put it in negative x squared, which is negative 1 to the n times x to the 2n. So that was the one that was 1 minus x squared plus x to the 4th minus x to the 6th, so on and so forth. We could integrate both sides of this equation. That's just another tool you have that you can do to both sides of an equation. Okay, so the integral of this, which is just arctan, that's the whole point of it, should equal the integral of this. Now we haven't, when you're differentiating and integrating a power series, you're just doing every term. So maybe it's easier for you just to write out some terms of these and integrate them right? Because this is like 1 minus x squared plus x to the fourth. So the integral is going to be like x minus x cubed over 3 plus x to the fifth over 5 minus x to the seventh over 7. You already see the pattern. Or you can just do that generically. So when you integrate this, it doesn't matter if you put the integral inside or outside of the sigma. Looks like a lot of Greek though, doesn't it? Negative 1 to the n is just a constant that comes along for the ride. To integrate x to the 2n, you just add 1 to the power and then divide by that same quantity. And that's what you would see if you just started to integrate some of the terms of it. This is just odd powers of x over odd numbers, and they alternate. So this original series alternated, its derivative or its integral is also going to alternate just because constants come along for the ride. Okay, so there they are. So you see what I'm saying? It's odd powers of x over the same number, and they alternate. Your book has a very beautiful formula that involves this power series for pi. There's a series that equals pi, and it's a very simple series. It's like the closest thing we have to pi not being just completely transcendental. And it's because of like what the tangent of pi over 4 is. Okay, I didn't include it, but look in your book. It's beautiful. Okay, so the green thing is arctan. Remember what that thing looks like? And the red thing is the first 5 terms of our odd polynomial. Literally odd. Notice that. The function's odd, its power series is odd. Whoa, what a coincidence. Nope, not a coincidence. It works. And you can just see that in here, at least, right, if you zoomed in, the green and the red graphs are very, very, very similar. In fact, they're exactly the same. And the more terms you add, and notice, right, it's between -1 and 1 again. And this thing, I think, does converge at the endpoints, which is what gives you that beautiful formula for pi that I'm not explaining. All right, one more. And this is not a hard one, but you'll kind of see why, one of the reasons why we care about these funny things, these infinite polynomials. So find a power series for 1 over 1 plus x to the 7th. So this is actually just like the first example we did. We're just going to take the original thing, the power series for 1 over 1 minus x, and just replace it with something else. So that's our established thing that we've been dealing with the whole time. You might think, like, is this like the mother of all power series? No, but kinda. And so you see, now we got to make this look like this. So once again, we just replace x with negative x to the 7th. And that'll do it. And then to do that to one side of the equation, you have to do that to the other side of the equation. Okay, so the left side is 1 over 1 plus x to the 7th, and the right side is -1 to the n times x to the 7n. So it's exactly like when we did it before with negative x squared. So much so that you're like, why are you doing another example? Well, there's a good reason. You'll see in a second. Shut up. Okay, so this is, again, it's helpful to write out some terms. This is like 1, so this is 0 minus x to the 7th plus x to the 14th minus x to the 21st. So right away, you see the pattern. It's just a polynomial, just only with multiples of 7 numbers. Again, why 7? Well, because it's weird and interesting. Here are the graphs. The blue thing is 1 over 1 plus x to the 7th, because this thing does have an asymptote when x is -1. And the red thing is the first, I don't remember how many terms of the power series. So this is a very weird shaped function because of the oddness, literal, of it. And it's a very weird shaped power series because it's a weird, odd polynomial that only has powers of 7 in it. But you can see that, you know, they go together. They're weird in their own precious way. Okay, and that essentially serves as a check. If you did it right, the graphs match up exactly. If you didn't, they don't match up at all. Okay, so here's where it gets interesting. Well, I think the whole thing's interesting. Find a power series for the integral of 1 over 1 plus x to the 7th dx. Now, you may be thinking, well, why do we need a power series for that? Can't we just compute the integral? Well, can you? I'm genuinely asking. Do you know how to do this? And now, it's kind of a joke question because you don't. I don't either. it is insanely complex, and I guarantee no one knew what the integral of this was before we had computers. I guess I don't guarantee that. Maybe Euler or somebody did, or Gauss. Okay, so I'm going to show you what it is. So the point of doing this is that it's impossible to do the other way by hand. So here it is that I literally just copy pasted off the internet. Don't write that down, okay? That's it. That's the actual integral. So everybody agree with me. We don't want to do that. We don't want to know why that is, how they got that. It looks like a joke. It's got every single type of function you've heard of. It's got natural logs. It's got inverse trig functions. It looked like the kind of answer that would show up on a test if you cheat on a Calc 2 exam by plugging it into Wolfram Alpha. Right? I would have to mark it wrong because I'm like, there's no way you figured that out. I think it would just be like a nested partial fractions thing if you were gonna, but we're not gonna. Okay, so just marvel at how nasty that is, and let's do it our way. All right, so that's impossible, but since we have a power series for it, integrating a power series is literally just integrating a polynomial. It's the first thing you learned how to integrate. You're just using the power rule. Right? There's almost nothing to it. You do it before breakfast. It's a piece of cake. So when you integrate a power series, it's just x minus x to the 8th over 8 plus x to the 15th over 15 minus x to the 22 over 22. So it's just one more than multiples of 7 over the same number. And then we can obviously write that out in series notation. I will probably want you to do both. Ultimately, I'll probably want you to leave your answer in series notation because I want you to be able to, I want you to know how it works. But it is almost easier to comprehend looking at it like that because you just kind of see the pattern. But the whole point is that that's just a polynomial, right? It's just a normal polynomial except with infinite terms, so it's a power series. And what I'm telling you is that that exactly equals that hideous function I showed you earlier that is like the closed form of this integral. Okay, so only within -1 and 1. It doesn't converge elsewhere. There's not some other thing that does. Don't worry about it. This nice, relatively nice looking function, it just has infinite terms, but it's just a polynomial, exactly equals the insane thing I showed you from before. Okay, so really that's our first, I guess, application of these things in the real world, is we have functions that either have insanely complex integrals or functions that are have non-algebraic integrals that don't have integrals. They don't exist. But they have a power series, and every power series has an integral because it's literally just a polynomial. So we can integrate things that there's no other possible way to do it, even for a computer. Okay, so that's a cool thing we can do with power series. So in the next lecture, we'll answer the question, does every function have a power series? And the answer is kind of. Okay, thank you.